Hey BC Calc students, I know you don't usually start a video by seeing me to start, but today we're going to be taking our notes for day 42, which if you look at the title are Riemann sums and what are called definite integrals. Now I know that some of you have some experience with integrals already if you're taking physics currently, but I just wanted to give you a quick heads up. Today is very theoretical. So you're going to see a lot of different notation, a lot of generalized cases. And for that reason, some of today might be somewhat abstract for you. I promise it will get more concrete at the end and into the next few lessons. But all I'll ask is as you're kind of following along with today's notes, I just have a lot of kind of ideas and notations and things about our diagrams filled in next to some of the pictures that you'll see in the notes in the margins. So maybe kind of copy those things down. And of course, if you have any questions, you'll check in with me next time we're in class. So let's get started on those day 42 notes. I'm going to switch my camera over. And as a quick review, in our last lesson, we learned about RAM, the rectangular approximation method, for the first time as a way to start thinking about approximating the area under a curve. So here are our three cases that we've really studied so far. So if we want to find the area under a curve from A to B, we have these options. We have LRAM, we have RRAM, and we have MRAM. So the left rectangular approximation in this instance is going to be inscribed rectangles, all contained underneath the curve. We know that if the curve's inflection was going the other way, LRAM would actually be circumscribed, like RRAM is for this example. Okay. And then MRAM, what we saw in the notes yesterday is that if we take the midpoints of these subintervals and determine that as the height, MRAM is kind of nice in that you get a little bit of an overestimate, a little bit of an under, and those might balance each other out well to be a nice approximation for what the area under the curve is. So just kind of a quick visual going back to what we learned in day 41. So today we're going to consider, again, many different diagrams, and we're going to start building a little bit moving away from these exact RAM models of LRAM, RRAM, and MRAM. So for example, the first diagram on the left side here is actually not LRAM, right? So it looks like we're at the left endpoint here, but we're definitely not at the left endpoint of this subinterval from A to this value right here. So it's not LRAM, but these are in fact inscribed rectangles in under the curve y equals f of x. So based on the inflection of that curve, you know, LRAM, if you wanted inscribed rectangles, it doesn't exactly match up with what LRAM would be in this case. And if we extend those inscribed rectangles out a little bit further, here's some more rectangles, right? Well, I would say that if I sum up these areas of these rectangles, that's going to be a little bit more accurate. I mean, look at all the space that we're not capturing with just two rectangles. That's no good. So if we extend it out a little bit further, yeah, there's still some gaps here, but not as many gaps as what we had with just two rectangles to start. And then we kind of move on to the bottom. And yeah, I mean, the more rectangles you have, the more accuracy you're going to have in capturing the area under the curve y equals f of x. So if you think about what this is a concept mathematically, the more rectangles we have, the more accuracy we build for the area under the curve. Think about a mathematical concept of, you know, approaching a certain number of rectangles and how that really truly can approximate the area that we're looking at here. Okay, so what if we don't look at inscribed rectangles, but similarly we look at some circumscribed rectangles. So if you look at the example at the top of the next page of the notes, well, these are not inscribed, but they are circumscribed, but it's not RRAM, right? So here's the right endpoint, right endpoint, right endpoint. This might be the right endpoint, but this one's not, right? The right endpoint here would not be this last rectangle, okay? These are all circumscribed over those subintervals that are defined here from A to B, okay? So once I see that, then I can say, okay, well, more rectangles again, right? That if I break this up into even a smaller partition here, the areas of these rectangles, there's a lot of overestimates here, right? And the overestimations here seem like they're going to be a little bit less than what we have when we only have 5 rectangles. And certainly, you know, we're definitely building here towards, wow, now we have a ton of rectangles. And those little parts that are above the curve, those circumscribed pieces of these circumscribed rectangles, yeah, I mean, those are going to be tiny little areas, but it's better than the area that we're getting up here. We had much larger widths. Now, remember that we defined the width yesterday, those delta x's, as being b minus a divided by n, where n is the number of rectangles that we have, right? It's the difference of your start and end values that you're trying to find the area between divided by the number of rectangles. So the concept here is as n gets bigger and bigger, the number of rectangles, what's happening to delta x? Well, as n gets bigger and bigger and goes to infinity, right? That's what we're building towards here. Delta x is going to go to 0. So if that delta x value is getting closer and closer and closer to 0, then we're actually approaching what the area under the curve is. Okay, so the more rectangles we have, the more accurate we have. And if we think of this as a concept of the number of rectangles approaching infinity, we're going to get what the true area under the curve is. Okay, so then we're going to move on to this diagram over here. And what's going to start happening now is rather than just having inscribed or circumscribed rectangles, these are all looking inscribed. But I mean, based on the curve, you can see that these are not necessarily LRAM, they're not necessarily RRAM, but notice how the heights over these subintervals are all at different locations. So the height of the first rectangle over here is at C sub 1, but the next height, C sub 2, is going to be right here for this rectangle. So it's not a left endpoint, it's not a right endpoint, it's kind of like somewhere in between. And look at this last rectangle over here, the C sub n, right? So the height of that rectangle over here occurs, again, somewhere over the interval. So we're not only going to start looking at exactly inscribed and circumscribed and LRAM and RRAM, we're going to start looking at rectangles drawn underneath that are drawn at varying heights along the way. So if I were to write as an expression to represent the area under the curve here, the heights can be taken anywhere. So you're going to get that the area is approximately whatever the height of the function is here times that delta x, plus whatever the height of the function is at C2 times this delta x, and so on and so forth, right? We build all the way into the last case where the last height is at f of C sub n times this delta x, and that represents the sum of all the areas, S sub n. So therefore, if we build that one more step out, connecting it to what we set up above, if we take the limit as n goes to infinity of S sub n, that would be the limit as n approaches infinity of the sum of all the rectangle areas, right? F of C sub I from I equals 1 to n, right? Take all of those heights, multiply by the delta x widths. And if I sum all those up and take the limit as n approaches infinity, that's going to represent the area under the curve. So we're going to build this out one step further from here then. Here's what we've got when we're looking at random heights. Well, if we have random heights, we can also have random widths. So if you look at the top of the next page, you can see that here's a bunch of inscribed rectangles, and the distance between x1 and x2 is much different than this distance over here for this width. So we're building this more generalized case that we don't necessarily have to think of it as LRAM or RRAM. To get the area under the curve, we can start also randomizing the widths that we see here. And there's one more piece that we have to add on before we truly define this sum here for the sum of the rectangles to represent the area under the curve. But this more generalized case that we're looking at today, here we're looking at a bunch of varying widths. And the last thing that we're going to add on here is, does it have to be all positive? Because every diagram we've looked at up until this point has been for a positive valued function y equals f of x. Well, of course it doesn't, right? I mean, here's a great example of that. Okay, here's a function that has some negative y values, some positive y values, and you can see that if you draw rectangles, some are going to be below the x-axis, some are going to be above the x-axis, depending on where you draw those heights. Okay, so this is even more random now. So you got varying heights, you have varying widths, and you have positive and negative. So for a final case here, if the area would equal, again, the sum of the areas of all these rectangles from I equals 1 to n, of our varying heights times our varying widths. Okay, so now our delta x sub I is what we're going to write here, since the width of the partition might vary. And those varying heights could be positive and they could be negative. So like I said, notation is super heavy in today's lesson. You know, for those of you that go on to take very high level, upper level college math courses, you know, this is for you today, because I think you would see notations similar to this in upper levels of calculus and differential equations and things of that nature. So it's good to be exposed to this at some point in this course. Okay. All right. So we've got all that. There's a lot of words on the next page. I'm going to read through them with you and hopefully make some sense. I'm going to refer back to this picture when needed. Okay. So for an arbitrary continuous function, y equals f of x on the interval from a to b, if we partition the function, so we're going to break up the interval from a to b into different widths, right? And we're going to define those widths at x0, x1, x2, all the way to xn, where x sub 0 is our initial value a, x sub n is the end of the interval at b. And then we're going to have these different intervals, x sub 0 to x1, right? So you can see that in the picture. So we have the interval here, x sub 1 to x sub 2. You know, eventually we're going to have x sub k minus 1 to x sub k, x sub n minus 1 to x sub n. So we get all our subintervals, and then on the kth subinterval, we select some c sub k. So what is c sub k? C sub k represents the height. Okay, that x value where we're going to draw the height at. Okay, so f of c sub k actually is going to be the height there, but you're going to select some value, c sub k, such that the area of each rectangle is now f of that height, or that value of x, f of c sub k times delta x sub k, the width of the interval at that value of k. And just a quick note that if this is less than 0, that height, then we're going to get a negative area attached to that, which is a little bit of an odd concept, but we'll talk about this as we explore integrals a little bit further. So consider S sub p to be defined as the sum of the partitioned areas, right? So if I take all those partitions along the x-axis and then I find the areas of those rectangles, well then S sub p would equal the sum from k equals 1 to n of those random heights times those random widths. That is known as the Riemann sum for f on the interval from a to b. Okay, Riemann was a German mathematician who determined that this is the way to approximate the area under the curve and giving varying heights and varying widths. So if we move on to this next section, what we now want to think about is, well, how do I then take this from the sum of all those areas and kind of reduce it down to the true area under the curve? What we're going to think of is some sort of limiting process. And we're going to represent something called the norm of the partition P. It's the length of the partition's largest subinterval. So we have a whole bunch of subintervals drawn here, right? X sub 0 to x sub 1, x sub 1 to x sub 2. Well, what we can do is if we think about what is the largest subinterval, it looks like it's kind of over here in the diagram, right? Maybe it's this interval, maybe it's this interval. And if we take that largest subinterval and we take that width and we make it go to 0, well, if the largest of our subintervals goes to 0, then all the rest are going to follow suit, aren't they? All the other widths are going to shrink down to 0 as well, meaning that if you take the limit, this is the notation for the norm of the partition, the limit as that norm of the partition goes to 0 of the areas under the curve, that equals capital I. And what is capital I? I is called the definite integral of f over the interval from a to b, which is denoted using this notation. And this notation might look familiar to you. I'm sure it does for many of you already. Like I said in the beginning, if you're taking physics, even if you're not taking physics, I know a lot of you are familiar with that integral notation. So this is read as the integral from a to b. And this is going to make a lot of sense. Why do we use this symbol to represent area? Because Leibniz used this notation because the integral sign looks like an S. And what are we doing? We're summing up a bunch of areas. So that's kind of cool. Okay, so kind of bringing it all together. How do we define the definite integral? Capital I. So the limit of the norm of the partition is that widest partition goes to 0, so do all the others. Okay, if we sum up the area of all those rectangles, we're going to get that that's defined as the integral, the area under the curve from a to b of our function f of x. Okay. So going to the last page here. So, and I know this is like super notation heavy and super theoretical, but we finally get to do a little bit of math at the end of the lesson here. The integral existence theorem is exactly what we just talked about. If f is continuous on the interval from a to b, then the integral from a to b of f of x dx, okay, where dx are all those widths, right, is the limit as the norm goes to 0, okay, that largest partition goes to 0, of the sum of the areas exists and is the same number for any choice of the numbers c sub k, okay? So that theorem should be in your textbook. What we're going to do is actually just practice evaluating definite integrals with Math 9 on the calculator. So just like we have Math 8 for numerical derivatives, we can do numerical integration by choosing Math option 9. And you'll see that the inputs are the following. That we're going to type a lower bound on the bottom end of this integral. We'll type the upper limit. Okay, so these are the values of a and b. We'll enter the function in here, and then we'll have to make sure that whatever function we enter in here, in a lot of cases, 99% of the time, you're going to put an x there because that's the variable we're integrating with respect to. Okay. All right, so let's just make sure we can practice with Math 9 here. So Math 9, here it is. So if I want the area under the curve from 0 to 1 for the function 1 plus x squared dx, so that's going to be 1.3 repeating. All right. So this is the nice and easy part of the lesson. Okay. Or if you want to express that as a rational value of 4/3, we can do that pretty easily. Okay. I think you'll start to find some interest in these questions here, right? So now we're going to get into area under trig functions. So if I do Math 9 from 0 to pi of sine x dx, okay, we get that the area under that curve is 2, exactly 2. So that's kind of interesting. Area under the curve from 0 to pi is 2. Now, if you think about what the sine curve looks like, what do you think is going to happen from pi to 2 pi? Well, isn't the sine curve kind of the equal area on the other side? But will it be the exact same answer? I don't think so. Because think about those heights that are going to be drawn to the curve from pi to 2 pi. How do the heights differ from 0 to pi? Well, they're going to differ in that, aren't they all going to be drawn below the x-axis? The sign goes negative from pi to 2 pi, so now we get -2 as an answer. Okay, so these areas might turn out to be negative if it's a negative valued function, or if it's negative valued for longer than it's positive valued. Okay, so then what would be the total integral from 0 to 2 pi here? If I go from the start here to the finish line there, what's that going to come out to be? Well, if I take the area from 0 to pi and then the area from pi to 2 pi, does it make sense that the total area here is going to come out to be 0? All right. Yeah, this is an accumulated area. So we added up from 0 to pi. That was 2 above in terms of area. And then we had an area of 2 square units below, which counts as -2. So the accumulated area from 0 to 2 pi of sine x dx is 0. So that's kind of weird. So we're going to have to differentiate between what we mean by accumulated area and then total area. And we'll talk about that in the next few lessons. All right. Well, what if I had done the same integral as number 3, but I put absolute value around that? Can you picture what that's going to be? That should just take your absolute value, your sine function, and take it and make all the y values positive. So this should become +2. You can double check it on here by putting absolute value around sine x and confirming that. I like number 6. So 6 is interesting in that if we do the definite integral from -2 to 2, we get a value that I think you'll recognize. Oops. So we get from -2 to 2, the area under the curve radical 4 minus x squared dx is 6.28318. And the reason why I think that number should look familiar to you is that if you think about what this curve looks like, radical 4 minus x squared is a half of a circle, right? So we actually know this area. If we take half of pi r squared, where the radius is 2, half of 4 pi is going to be 2 pi. So this is one where, if we go back to our lesson from yesterday, do we always need calculus to find the area under curve? In this case, no, not really. And by the way, based on the algorithm that the calculator uses here to find the area under the curve, you notice that it's slightly different in the decimal values at the end here, but it's a good approximation to give us that, yeah, this is going to be 2 pi. And then finally, for these last two examples, these are integrals that we don't know yet. Whereas if I come back here, we actually know what the integral of sine x is, and we could find the integral of 1 plus x squared. So we'll talk about how we can use that integral and these bounds in the next few lessons to be able to evaluate these areas. But we don't know what the integral of those are. So we really have to rely on the calculator. If I think about graphically what's happening here, from -1 to 2 for the function e to the x, we're looking for this area. So we know that it's a positive valued function always, so we will turn out to get a positive area here. So if we figure out what that is, and we'll go to 3 decimal place accuracy because it's not going to necessarily come out to be a nice answer. But if we do math 9 from -1 to 2 of e to the x dx, we get that the area there is 7.021. And eventually we'll have a way to be able to evaluate this without necessarily relying on the calculator when we learn about what the integral of e to the x is. Same thing for ln of x. Since we don't know the integral yet, you would have to do math 9 for now. So from 1 to e, this is going to be an interesting one as well. The integral from 1 to e of ln of x dx is exactly 1 square unit. So if you look at what the graph looks like for ln of x from 1 to e, the area here is 1. All right. So I know this is super theoretical, like I mentioned at the start of today's lesson. We're going to get a lot more practice with math 9 and finding the value for definite integrals given these two bounds in the future coming lessons here. If you have any questions about the theory that we talked about today, please let me know next time we talk in class. Otherwise, I think we'll be good to go and move on with evaluating of integrals. Have a great rest of your day.